Hello everyone and welcome to this lecture. In this lecture, we will see another very beautiful theorem that we call Cauchy Interlace theorem. It tells about some inequality of the eigenvalue of the original matrix with the eigenvalues of some principal submatrix. Okay. Remember 2-3 lectures before I mentioned about spectral theorem, and we have already seen many uses of this. Similar to that, this theorem also has many beautiful applications. Okay, and so let us start with this theorem, but before that I will be needing some kind of I will not say it's a warm up, but I will be needing one small result which is very trivial. Okay, and then I will be stating what this theorem is, and then we will go ahead with the proof. Okay, so the one thing that I will be needing is this. Suppose you have some matrix of order n cross n. Okay, if you permute some rows and the same columns, basically if you permute rows with some indices, if you permute the columns with the same indices, okay, the resulting matrix will have the same eigenvalues as before. The eigenvalues does not change at all. Okay, let us see why. Okay, so suppose you have a square matrix of order n cross n and you are permuting some rows and columns, right? The same row and same column. This is equivalent to multiplying on both sides. So on towards right maybe by some permutation P, and towards the left by permutation matrix P transpose. If you do not know what permutation matrix, very simple matrix which is actually permutation of the identity matrix. Suppose this is identity matrix, okay, of order n cross n. Okay, and if you want to permute, suppose if you want to exchange or row I and row j, so all you need is you exchange here. You exchange the row I here and row j, okay, and then you multiply towards left of a, right? And similarly, if you want to permute column I and column j, basically swap, you multiply the resulting matrix after doing the same operation here towards the right of a. Okay, so such matrices we call permutation matrix. Basically you are permuting the ones of identity matrix up, down, left, right. Okay, so this is permutation matrix, and this helps us in permuting the rows and simultaneously the column of our square matrix. Okay, we have to prove that the eigenvalues of this matrix are same as the eigenvalue of our original matrix A. How? Okay, let us quickly see that. Okay, so let us write, I mean there can be many ways. So one very trivial way is this. So suppose if you want to find the eigenvalues of this, right, so what you will do what you want to find its characteristic polynomial. Okay, so suppose this determinant of it. Okay, but I can write this matrix as this, right? I mean this thing I can write as determinant of P transpose A minus lambda I times P, because due to this, right? Very simple one. And by the way, this, if you do this, the P transpose P equal to P transpose identity. Okay, this comes from the definition itself. Okay, so this is again another orthogonal matrix. Okay, very good. And then what? You just apply the determinant rule. This is equal to determinant of P transpose times determinant of A minus lambda I times determinant of P. You can take this side, but you know the P into P transpose equal to identity. So that means you can write this as, so these two quantity will actually give you 1, right? And this is then equal times determinant of A minus lambda I. So this is equal to determinant of A minus lambda I. Okay, so both of these guys will have the same eigenvalues. Okay, same roots of correct. Okay, nothing. I mean, you can prove it using a different way also, but just by, in fact, you can find the eigenvectors also in terms of the eigenvector of the original matrix. Suppose Ax is equal to lambda x, right? Ax is equal to lambda x. You can actually write this as A, and then maybe P transpose, or maybe, I mean, other way also, that will be look much more appealing to see. So P into P transpose x, right, because this is identity matrix, and do the same thing here, x P into P transpose here, and then you can multiply towards left, right, P transpose here, P transpose here, right? Sorry, this is lambda here. Okay, so yeah, so lambda, and then P transpose here, right? And this quantity will become one identity, and this, you see that this matrix will have eigenvector this corresponding to the same eigenvalue, so this is equal to identity. You are getting the eigenvector. And its other way also is very, very simple. So suppose, so this tells that if lambda is eigenvalue of A, lambda is also eigenvalue of P transpose AP with eigenvector P transpose X. Okay, other way is what? Suppose P transpose AP has eigenvector X with eigenvalue lambda, then you can actually immediately see that this matrix, you multiply on both ends side by P transpose P, right? So like here, so P into P transpose APX will give you lambda times PX. That means, and this becomes identity, though this implies that APX equal to lambda PX. So again, lambda is an eigenvalue with eigenvector Px. Okay, so very, very, so two simple proofs. Okay, now let me state the Cauchy interlace theorem. Okay, it will be shortly clear why we call it interlace. Okay, so let me first write the statement. Very, very beautiful theorem. Okay, theorem Cauchy interlace, Cauchy interlacing or interlace theorem, interlace theorem. Okay, Cauchy interlace theorem. Okay, very good. Let M be a symmetric matrix of order n cross n, and B be a principal submatrix, be its principal submatrix, maybe it's correct, be its principal, be its principal submatrix of order m cross m. Okay, let me write down the eigenvalues of, let lambda 1 greater or equal to lambda 2 greater or equal to lambda n be the eigenvalues, be the eigenvalues of m, and beta 1 greater or equal to beta 2 greater or equal to beta m be the eigen values of B, then the statement is this. Then the statement is, yeah, lambda k is always greater or equal to beta k, which is always greater or equal to lambda k plus n minus m. Okay, here the m is, of course, I mean, this m is of course less or equal to n. Okay, so very obvious one, where k equal to 1 to up to m. Okay, very, so this means that the eigenvalues of principal submatrix are are sandwiched between the eigenvalues of the original matrix. Okay, principal sum matrix means you are choosing the same rows and same columns, right? If the indices of rows are basically the indices of rows and columns are same. Okay, very good. So let us prove this beautiful fact. Let us prove this beautiful fact. Okay, so very good. So let us go towards the proof. Okay, to start with, I will be having a cheating, but it's not exactly cheating because I have already proven the thing that I will be just writing down. Okay, so I can write M as this. So suppose B is my this matrix. Okay, remember I am writing B as a top left corner. Okay, basically first M rows and first M columns, right? Remember, by permuting rows and columns, I can the eigenvalue does not change, right? So whatever the principal sum matrix, by changing the rows and columns, I can take it to the top left. The eigenvalue is still the same, so I can safely write this. Okay, so M is equal to this. Basically, I am saying that the statement also hold the eigenvalue statement is pretty much okay with this setup. Okay, then there may be some for some x and for some suitable x and z matrices. Okay, I can write this. Okay, so let M equal to this. Then I have to prove that, and I have already done the eigenvalues of B are this, right, and eigenvalues of M are them. Suppose the eigenvectors of M are, let me take x1, x2 up to xn, right, corresponding to being 2 lambda 1, lambda 2 up to lambda n. Okay, and similarly I mean, okay, and the same thing, the eigenvectors of B are y1, y2 up to yn. Let me put some more dot. ym corresponding to beta 1, beta 2 up to beta m. Very good. Okay, so, and my target is to achieve this. How can I prove this fact? Okay, let us first try to prove that lambda k is always greater or equal to beta k for any k equal to 1 to m, right? Okay, how can we prove this? Okay, so let me make some linear combinations, or what we call a span or vector space. Don't get confused by these terms, very easy. Okay, suppose let me make some linear combinations of these vectors. Okay, x1 up to xn and then y1 up to yn, and let us see what follows. So suppose V is, where is pen? Okay, suppose V is, or maybe I will so V is actually the the set of all linear combinations of these vectors. So let me call these vectors, since I have to prove that lambda k is always greater or equal to this. Okay, so let me say that lambda vector xk plus 1 and dot vector xn. Okay, and set, so this V is actually set of all linear combination of these vectors. So this we call also a span of these vectors. Okay, very good. And similarly let me call a vector linear combination of all vectors of y1. It will be clear why I am making such crucial with span or linear combination y2 up to yk. Okay, again this is span of this, right, is span of these vectors. Now see that very crucial observation here. The lambda k is nothing but maximum over all vectors that belongs to this V x transpose x. This is actually very easy observation to see. I have proven it when I was proving some eigenvalue, the largest eigen lambda 1 is the largest eigenvalue, and how we can represent the lambda 1 in terms of this such quantity, right, x transpose. Similarly, lambda n is the smallest, and I have represented using s transpose x, the minimum over that, right? Okay, the maximum over all that, right? Similarly, if you see that this beta k is what? It's actually minimum over all y transpose by here, because we have to use this b. So very clear here, let me write. So by divided by where y belongs to this space. Very easy observation, very easy observation. Okay, now let me cook one more vector space, or I mean just a space, right? This is called actually span or space, whatever you want to say, which is actually set of all vectors where of this form. Basically this vector, I want to basically append to these vectors some zero such that the resulting size is in Rn. So suppose this is in Rn, where belongs to small w belongs to this. I hope this is also clear. This is again a span or space, right, where I have kind of added some zeros to make the size equal to the vectors in V. Okay, the size of these vectors is equal to vectors, so they are in Rn. Okay, now if we see it carefully, and any vector, okay, so what will be the rank of these basically these vector spaces? How many linear independent basically vectors are there in V, W and W tilde? Okay, so if you see carefully the rank or the number of linear independent vectors here, rank of W tilde is same as rank of W, which is very clear because we are just adding zeros, right? And what is this? This is nothing but k. Very simple, because there are only k linearly independent. I mean, you can say that these are full one, so k linearly independent vector. Okay, very good. What about V? Rank of V. Rank of V is nothing but n minus k plus 1. Okay, and remember both of these vectors are in Rn, or vector spaces are in both W tilde and V are in Rn. If you add these ranks, what will be the quantity? The number will be, if you add this rank, so n minus k plus 1 and k, that means the resulting n plus k. This implies, because the rank is exceeding n, right, this implies there has to be a common vector which is lying, basically common vector in W tilde and V. So there exists, this implies anyway, let me write, so rank of W tilde, so let me write with bigger one, okay, W tilde plus rank of V is actually n plus 1, right? Coming out to be n plus. This implies there has to be a common vector because the rank, these both are in Rn, right? So this implies there exists a common vector, a vector, I would say, a vector W tilde, okay, in both, right, in vector W, and what will be the nature of, because W tilde also is in W, so the nature will be like this, so it will be something, let me call it W tilde again, okay, and let me call it hat, or what should I say, I mean, anyway, it's okay, so kind of, no need to confuse here, so some W, okay, vector W which belongs to W and also V, okay. Now the things will be very easy. What will be the equation if you write, what will be this quantity W tilde not actually M times W divided by, if you do this quantity W tilde W, so this will be indeed given you, if you see it carefully here, the way we have written M, this is nothing but, this will be equal to W divided by, okay. Now I think the things will be very apparent to you. This quantity, so lambda k will always be greater than this quantity, okay, because lambda k is always the maximum of any vector x, and x, so this you treat this as x which is belonging to V, right, which is belonging to V, and this quantity is actually more than beta k, because beta k is minimum of all these, this ratio for all y which belongs to W, right. Here if you see that, so this here, if you see this W actually belongs to this bigger W, okay. So very good, so I hope this is clear now. So lambda k is greater or equal to beta k, okay. Now in the similar way we can prove the other inequality. The other inequality is what? So we have to now prove that. Now the second thing is we have to prove that beta k is greater or equal to lambda k plus n minus m. I will be similar to earlier, I will be again cunningly make those vector spaces. So let me now cook those vector spaces as this. So V is, now since I have to make that, so again span of, now tell me, I mean just think what will be the vector space I will be taking. I mean very cleverly, okay. So now since I have to make use of this, right, so what I will do is I will take vectors like, so x1 x2 up to this xk plus n minus m, okay, and now I will be maybe speed up bit, so W will be nothing but span of, okay, because I have to make it greater 1, so this is basically what, yk comma yk plus 1, okay, and up to ym. Very good. Now in the earlier one I can write that lambda k is, from here I can clearly say that lambda k plus n minus m is equal to minimum of all x transpose a or m. I think I have made use of a, no, yeah, so please be careful, this is m, right, this is m here, sorry about this, again sorry about, because I am making this writing mistakes, again this will be m, right, sorry, so minimum over x transpose m x divided by x transpose x, and this quantity will be here. This will give you, yeah, so this will give you that beta k here is equal to maximum of y transpose m my divided by y transpose y. Now I will be kind of quickly going over, I mean, because I will be following the same pattern. I will be again cooking some w, which will be w tilde, which will be consisting of vectors like w0, where this will belongs to Rn, right? This will belongs to Rn, and w here belongs to w. Okay, then rank of, what will be the rank of v? Rank of v here will be, what will the rank of v is nothing but k plus n minus m. What will be the rank of w tilde? Rank of w tilde will be same as the rank of w, which is here m minus k plus 1. M minus k plus 1. If you add these rows or add these ranks, sorry, so this will be again rank of v plus rank of w tilde is coming out to be, if you cancel this again m plus 1. So this implies there exists a vector w tilde which is of form this, right, w0, right, which is in both, which is belongs to w tilde and also v. Okay, now again do the same trick as I have done earlier. So what will be this quantity? So w tilde transpose m, w tilde divided by w tilde transpose w tilde, this will be equal to the same thing, w transpose b w b, yeah, what, okay. Now this quantity, if you see here from here, so beta k is, so now here if you see, now compare these two quantities here, x and this, so beta k is always greater or equal to this number, right, because of this, because it's a beta k is maximum over all this ratio. Okay, and this quantity is always greater or equal to this quantity lambda k plus n minus m. So lambda k plus n minus m. So this implies that indeed beta k is greater or equal to lambda k plus n minus m, and let me complete this, completely write and hence lambda k is greater or equal to beta k equal to lambda k plus n minus m for all k equal to 1 to up to 1. Very beautiful result, and we will see applications of it now this lecture onwards. Okay, so thank you very much and see you in the next lecture.